So we've talked some about how routers communicate and how they actually set up routing tables and how they determine the best way to get from point A to point B. Well, let's take a look now at some of the more specific routing metrics that they use. Now, when we're talking about routing metrics, we're talking about qualities that our routers use to determine the best path. When you hear metrics in computing, a metric is a measure of something. It's a analysis of how long it takes to get somewhere, how many other routers we have to hit, how much delay there is. A metric is a measure of something. So a routing metric is a measure of a different quality that we use to determine the best path. Now these different metrics are used when we're talking about our different protocols and when we're determining the best path to use. So it's important to know how these metrics are what is measured and which metrics we use when we're determining the best path. One of the most obvious metrics we use is going to be hop count. Now a hop count, as we discussed a little bit earlier, is essentially how many places, how many other routers, how many stops we go to before we get from point A to point B. Is it just a straight shot from our router to the next router to the server, or is it our router to Comcast's router or Verizon's router to another router in a different state to a third router to an intercontinental router to finally to the server that we're trying to get to? So it's important to understand those hop counts. And our hop counts, we can see which path we're taking, which hops or which locations we're hitting using a command called traceroute. Now traceroute is spelled out trace-RT, and there's actually no space. If we open up a command prompt and type in trace-RT space and then a server name or an IP address, so trace-RT 8.8.8.8, then we'll actually see the route that we take in order to get from us to that other location. And that traceroute command will show us all the different hops that we're hitting to get there. So all the different routers, all the different places we're hitting in between us and there. So that's our hop count. Next we have our MTU. Now MTU stands for maximum transmission unit. A maximum transmission unit is the maximum size of a single packet that we can send. So when we're talking about packets, we're talking about the amount of data that we can fit into one box. So think of MTU, a maximum transmission unit, as being the largest box that we get in order to fulfill a shipment of bricks. So if we're trying to send someone all the bricks that they need to build a house, then it would be better if we had larger boxes to send than smaller boxes. Our maximum transmission unit is going to sort of be our boxes in this scenario. We have all these bricks we need to send, and our MTU we are evaluating two different shipping companies for us, and shipping company A says, oh yeah, here's the largest box you can use in order to ship these 2,000 bricks. And they hand us a box about yay big. And we say, I'm going to have to send about 200 of these boxes, probably even more. I'm probably going to have to send about, 200 to 300 of these boxes to get everything through. And they say, yeah, we know. That's the biggest box that we can put on our trucks. And so we say, okay, what about shipping company B? And shipping company B says, okay, I've got this giant big box here that you can put all of you can put in 100 bricks at a time. We say, that's what we're talking about. That's what we need. We need a larger MTU. We need a larger maximum transmission unit to get this packet through. When we're talking about MTU, though, there's another concept we need to know about, which is bandwidth. Now, bandwidth is what's sort of limiting our MTU. And bandwidth is the width of the data that we can push through on a single link link at once. So it's the maximum amount of data that we can handle, either because of the port that we're connecting into, the bandwidth maximum because of our internet service provider, the bandwidth maximum because of the cable type that we're using. Our bandwidth is going to be the max amount of data that we can essentially push over a single link at once. So if we have a router that says, oh yeah, my maximum transmission unit is huge, but my bandwidth is really small. So I'm going to allow you to try and push through these massive packets, but my bandwidth is really going to throttle down what you can use, and it might even chop up some of your packets. We don't want that. Very large MTU on a small bandwidth isn't a good thing. So now we have shipping company B that said, yeah, I'm going to give you this giant box that you can use, but the thing is, we only have a couple trucks in our fleet that can really hold that box. So between here and where you're sending, we may actually have to open up that box and break up your box into different boxes, and then when it gets to the other end, put those boxes back together. But it's okay. Well, they may lose a box. Those boxes may get stuck around, or they may get delayed. So a large MTU on a low bandwidth isn't really a good thing. So we're evaluating our maximum transmission unit as well as our bandwidth on certain links when we're checking our routing metrics. Additionally, we're also evaluating costs. Now, when we're talking about costs, we're not necessarily talking about monetary costs. We're not talking about money here. We're talking about reliability, round trip time, costs as far as what it takes or how long it takes for our packet to get from point A to point B. This may include things like reliability. If we have a router that isn't always available or is kind of sporadic and sometimes goes down, sometimes is up, sometimes is down, sometimes is up, then it doesn't have a very high reliability rating. It's not very good there. Or we have a round trip time which takes a long time to go to one place and then come back to us. It's going to be a high round trip time. These are going to be costs that we have associated with that particular route. Now, if we're talking about a particular route or we're talking about a particular link and we say that it has a low number cost, lower number cost is good. Just like when you go to the store and you're trying to buy something. If you can get a good quality item, you can get the same item. You have two of the same items here at a lower cost, that's good. A higher cost is bad. So low cost is good, high cost is bad. And then lastly here we have latency. Now, latency is the amount of delay that we have on this link. And when we're talking about latency and we're talking about delay, a lot of times we're talking about how long the distance between one point and another, or how long it's taking for that other point to respond back, or how long it's taking for us to get there. Now we have this little guy drawn here, and this isn't a TIE fighter, it's a satellite, but I do my best. And when we think about latency, we think about satellites because when we have our phone, or we have a mobile hotspot, or we have a device or we have a GPS, or we have a internet connection which is connecting to a satellite, we're getting a very direct, high bandwidth connection from point A to that satellite. And compare that to if we plug our laptop directly into our router, we may actually even have less hops than if we just had a satellite connection to an internet service provider and then that satellite beamed down to their internet service provider's office. So there may be a lot of these costs or a lot of these metrics which look better in the case of satellites. We may have a lower hop count. We may have a higher MTU. We may have a higher maximum transmission unit. We may have a higher bandwidth. We may have more data that we can send at once. But our latency is what's really going to kill us. Because whereas when we have a cable link into a router or we have a Wi-Fi link to a local router that's going to be a wired connection to an internet service provider, our satellite connection is going to have to go from our location on Earth all the way to a satellite, then all the way over to the internet service provider. And then when the internet service provider gets the information to send back to us, it has to go from them all the way to the satellite and then all the way back to us. That's latency. So it's taking a long time. We're going to have a lot of delay on that link. So that's why if, say, you have satellite internet and you're trying to load a page, you may see your initial search. You sit there, you wait, and then boom, you get a bunch of data. Because you may have a high bandwidth. You're getting a lot of data at once, but you have a high latency. It's taking a long time for that chunk of data to get to you. You have a shipping company that is delivering a giant box at your door, but instead of taking 2-day Amazon Prime, it's taking a month to get to your door. So in the time it takes for you to get that one big box, you could have shipped 50 smaller boxes. And could have added up to more than that, twice as much as that one big box does. So that's why latency is also a big issue. So we want to keep that in mind when we're talking about our different routing metrics. So routing metrics, qualities used to determine our best path. We have our hop count, MTU, maximum transmission unit, our different costs, and our latency. So now let's take a look at some of our different ways that we actually determine our connection. So next we have our link state, distance vector, or hybrid. Now link state, distance vector, and hybrid all refer to protocols and different protocol types that our routers use in order to determine the best path. Now we have a lot more specific protocols that we'll get into and the specific metrics that those protocols use. But when we're talking about our protocols that our routers use, we have 3 main protocols that we break those into. And that's link state, distance vector, and hybrid. Link state is a cost-based protocol. When we're talking about routers that use a link state protocol, they are using metrics such as our costs here. So they're going to use costs and latency, MTU. They're going to use that cost-based, how much effort, how much time does it take for me to take this packet and get it from point A to point B? That's going to be MTU. That's going to be our link state. An example of a protocol that uses link state is OSPF, Open Shortest Path First. That's a link state-based protocol. Then we have distance vector. Distance vector protocols are just based on hops. They are just based on the distance, the number of hops that it takes for me to get from point A to point B. If I have a way that I can get to this location and it takes me 1 hop, and I have a way that I can get to this location and it takes me 2 hops, I'm going the way that it takes me 1 hop, because that's what distance vector does. It just bases it on hops. And examples of protocols that use this are RIP and RIP version 2. And again, both of these have their weaknesses, and especially distance vector. You can't judge a book by its cover. You can't judge a route you can't just judge a route by the number of hops it has. That route that has 1 hop versus that route that has 3 hops, that route that has 1 hop may have a super tiny MTU and a lot of latency, whereas that route that has 3 hops has a very nice large MTU, very high bandwidth, very low latency. So those costs and those distances can be rolled into our hybrid protocols. And our hybrid, just like our little hybrid cars that drive around, use the best of both worlds. They have our cost-based and they are hops-based as well. So our hybrid is going to be distance vector, and they're going to be link state, and they're going to use both hop count and cost in their analysis of which routes are better. So that's our routing metrics, our hop count, MTU, costs, latency, and bandwidth, and how we use those when we're talking about link state, distance vector, or hybrid routing protocols.